Okay, anyway, I do have it if you'd like to come. And this will give you an idea of the kind of thing that's in, so if you'd like to put in something for the 2017 calendar that's on the road. The membership for the national is now over 5,000. For the first time in its history, is over 5,000 people. So that's really great. Just as ours is increasing and is at the highest level it's been in a long time, so is the national level, which is really nice to see as well. We also have a new patron who is the Right Honorable David Johnson, our and so he is now the patron of the RASC and has signed his name. So we can now put him as one of our right legal patrons for the RASC. Again, trips from national. There is a national trip from the RASC that is going to be going to the eclipse. It's more in more to the east than where we would be, because they're coming down from Toronto and Hamilton and some of the places. So it's a little bit more eastern focused than ours is, but it is a full trip complete. Like you pay an amount and everything would be done for you. So if you're interested in that, that's online as well. They were talking as well. They had quite a nice trip down to Southern California back in the fall. They had that for the very first time that they did. They went to all different kinds of places and saw, we're going to some of the different sites with the telescopes. They were meeting with different people. They saw all kinds of things and they really enjoyed it. It was really good. And now they're looking at doing something to Arizona, so that they would be looking at some of the things in Arizona. So keep track of those as well. The other thing, I think the last one that I wanted to say was that you can and I don't know whether you know that, you can download the Observer's Handbook complete for, I believe it's $10. And you have to pay your money before you get the code to download it. But it can go right on your, it could be right on your computer, you're out in the field or that kind of thing. So if you're interested in that, we can also go to the e-bulletin. Maybe I can put that up on our website as to how to contact that. So if you're interested in that, I mean, we all love our handbooks, but you can actually have it right on the computer if you'd like to have that. So, okay, I think that's maybe all for you. Okay, thanks. Our next.
Anything else from anyone? Okay, so just a reminder, especially for the new people and visitors, that after our presentation, we generally retire to the Astronomy Lounge on the 4th floor of the Elliott Building for coffee and cookies and chat. And that's a good way to come and kind of meet us less formally than this. So just follow us up after the meeting. And so now we have our guest speaker for the night, which is actually quite exciting. Ozzy was born and raised in Iran. She studied physics after her bachelor's in Tehran, Iran, at the Sharif University of Technology. In 2011, she moved to UVic for her master's in astronomy and is transferred to the PhD program in 2013. So please welcome Ozzy Fatahi.
Yeah, that's crazy. It's multiple corners. Lots of different it's here, you're telling me the shorts here. Oh, yeah, good. I was kind of pleased with that. Yeah. Oh, you're gonna get some of the less of the currency because they're moving. Hopefully next week. Yeah. We're gonna they have different approximate values. No, I talk about the best. I know the restaurants.
Okay, and read. Okay, currently in the back. Okay. It's my pleasure to be here and get the chance to talk a little bit about my work. I have lots of interesting stuff. I hope I can cover all I want today. And we'll see how we go with the timing. And please interrupt me in the meantime if you have any questions. If I'm going too fast or too slow, we can adapt to how I'm going. So the title of my It's beautiful movies that I put in the presentation. So as the title of my talk says, I would like to talk about dwarf galaxies and what we can learn from dwarf galaxies, about galaxy formation and how the universe has been evolved. I'll talk about what you're seeing here, actually the simulation of the cosmic structure that I will go into details of what exactly we'll see in a few more slides. And because I would like to give you some background about cosmology, I would like to mention some key elements and observations that made basically the new cosmology we know of today. The cosmology that we know today is quite a new science compared to some other sciences like chemistry, mathematics, physics. It's been almost a century that we have been able to know something about how the universe has been evolved. So the theoretical basis of this new cosmology that we know of is the Einstein theory of general relativity. This theory has been, has been a breakthrough describing how the space and time behave in the presence of matter. But this theory itself is not enough to tell us what's happening in the universe. For example, the theory has the option that we would have a closed universe, we would have an open universe, or we would have a flat universe. It has the option that the universe will be expanding, collapsing, or static. Without making any observations and measurements, we cannot tell which is the case, what's happening in the universe. That's why making observations and measurements is critical for us to understand what's happening. I think the key, the first key observation that was made in the history of the modern cosmology was discovering that the universe was expanding. It was the work of Hubble that he published in 1921. This is Hubble with his office, and he saw that the further the galaxy is, the higher its gravitational speed is. It's basically telling us that the universe is expanding. And this was the basically critical observation that the universe is not static, as people used to believe for thousands of years, but it's actually evolving, and this evolution is basically expanding. At the time of Hubble, we didn't know if this expansion is accelerating at a fixed rate or decelerating. We just could observe basically more the local universe than the whole universe, and we would see that this line which shows the rate of the expansion of the universe, and it has the name of the Hubble. We call it Hubble constant. But this expansion of the universe had a very critical consequence. Well, you can imagine the universe is expanding. Play the movie backward. The size of the universe gets smaller. So it means if you go back in time, the size of the universe is smaller, everything is denser in the universe, and maybe you had done this experiment in the high school that if you make gas denser, its temperature goes up. So if you go back in time and the size of the universe gets smaller, basically the components of the universe, the gas and at least ordinary matter that we know of, get denser and hotter. And of course, the smaller the universe, the hotter that gas would be. This is where the idea of the hot Big Bang came from. That first of all, the universe was an extremely small, the universe had an extremely small size, and it was hot. This was the idea of the hot Big Bang, and there was a prediction that if you have this hot, dense gas at the beginning, and it's interacting with photons, and it must have some kind of radiation that we should be able to observe in the universe. But it was not until 1960s that in actually very accidentally, Penzias and Wilson find this relic radiation from the basically which was left from the time of the almost Big Bang, very early time in the universe. Penzias and Wilson were actually doing kind of an engineering experiment, but they suddenly found that everywhere they basically point their instrument or their telescope at, they see a very weak signs of microwave radiation from all over the sky, from every direction, isotropically from all the directions. And the physicists at the time, that they knew the idea of the hot Big Bang should have that kind of radiation, interpreted this data as the leftover from the Big Bang, or that very hot soup of matter that we had at the early universe. This is Penzias and Wilson, and that was the instrument that they were observing the sky. This is the whole map of that radiation. We call it the cosmic microwave background. Microwave because it's the radiation is at microwave wavelengths, which has a temperature of about 3 Kelvin now. For those of you who are not familiar with 3 Kelvin, it's almost minus 270 Celsius or degrees of centigrade. They saw that radiation from everywhere in the sky, but later on, as we had more advanced instruments, we could detect this radiation at a higher accuracy, and we realized that there are small, tiny fluctuations in this radiation. This is the map that you'll see here. There are basically red spots and blue spots. They correspond to very, very tiny fluctuations or up and downs in the intensity or temperature of that microwave background. These fluctuations are, call it very tiny. They are about 100,000 times smaller than the mean intensity everywhere, 100,000 times smaller. So we had to be able to detect this. And the distribution of these small fluctuations actually tell us very important things about the universe. I don't want to go through the details, but from how these basically fluctuations are distributed, we could tell if our universe is flat, what is the geometry of the universe. We could infer different components of the universe, dark matter, dark energy, and different. We can extract a lot of data from this map. I think that's why I think this is one of the another critical observation in the history of modern cosmology. And the next one that I'd like to emphasize was redshift surveys. The very first one was done in early 1980s. And what is being shown here is that you observe a patch of sky, relatively small patch of the sky, and what you observe is deep, and you have galaxies, you observe galaxies. From the velocity of the galaxies in that small patch of the sky, using the Hubble's law, you can easily get the distance to these galaxies. So this map shows you the observer is basically standing here. And looking back in time, well, you know the light has a finite speed, and it takes some time for light to reach us from the galaxy. So basically, we are observing back in time, and also some patch of the sky that you see. It's actually, I guess, it's declination. Right ascension in the sky. The first map, of course, was not as detailed as this one. But the striking thing that astrophysicists or cosmologists realize is that galaxies are not randomly distributed everywhere. There are patterns in these distributions. So whatever is going to be our model for cosmology, we should be able to reproduce these patterns. These patterns tell us important things, especially they could tell us how much matter exists in the universe. I think these 3 or 4 keys are big pieces of the puzzle of the cosmology. Of course, there were a lot of works done in periods of 50 or 60 years until we got our standard model of the cosmology, which is what I'm sure you all have seen before, but I would like to emphasize and explain it again. This is the whole history of the universe. We know that the universe started from a Big Bang, the hot Big Bang I told you about. It had a rapid expansion at the very beginning. We still don't know exactly why. We call it inflation. This inflation, or this very rapid expansion, stopped at some point, and the universe had its normal expansion after this point. The universe is expanding, and as the universe expands, everything cools down. That hot soup of gas that we had at the beginning cools down, and so structures can grow from the initial conditions. In this picture, about 70% of the universe is dark energy. That we don't know what that is. About 25% is dark matter. We know a little bit about it, but not much. And only 5%, I'm sorry, I'm not sure if you can see that back end, only 5% of the energy budget of the universe is the ordinary matter. By ordinary matter, I mean us, planets, stars, what we observe in the sky. These ordinary matters, or sometimes we call it baryonic matters, is only 5% of the energy budget of the universe. And the rest, 95%, we don't know much about it. I would like to mention that at the very beginning, you saw that there are some small fluctuations. There were some small fluctuations in the cosmic microwave background. There were also some fluctuations in the basically in that initial soup of matter, dark matter and ordinary matter, which was also mixed with radiation. There was a small fluctuations. As the universe grows and expands, these small fluctuations, because of the gravity, amplifies. So the structures that we see today is basically the amplification of those very small fluctuations back in time. And because, well, you will see the dark matter is dominant over the ordinary matter. We have 5 times more dark matter than the ordinary one. That's why the whole structure of the universe, the biggest structure of the universe, its evolution is dependent on how dark matter behaves. So the standard picture that we have from cosmology is called lambda CDM. Lambda is referring to this dark energy, DM is dark matter, and C is basic cold. Lambda cold dark matter, and I will talk about this coldness in a second. So how does the universe evolve in this picture? Actually, computer simulations have been super useful in this field because how things evolve in the universe are not easy to be calculated on the paper. You have to be able to use very large computer simulations to be able to say what happens in the growth of this structure. And I'll skip that one. This is what we'll see for the growth of the structure. This is early in the universe. Everything is almost even and homogeneous everywhere, but not exactly. There are tiny fluctuations. As the time goes by, you go from basically top left to the bottom right. You'll see the structure grows over time. You start from almost a homogeneous distribution of matter, but this is dark matter. Because as I said, the growth of the structure or the evolution of the structure is governed by dark matter. And you get basically a very complicated filamentary structure. There's also a movie of how this thing is evolving. Let's see. Okay, there you go. So this is a big, very big portion of the universe. This is 100 megaparsec, or 10 to the 6 parsec, and each parsec is 3 light years, almost 3.3 light years. So this is a very, very big portion of the universe. And if you evolve it using the computer simulations, you will see from the, again, almost homogeneous distribution, the structures grow. Now, let's see what these computer simulations are telling us. These cones are similar to another picture I showed you earlier. These are basically looking at galaxies through time, basically. If I don't tell you anything, you perhaps cannot tell which one is simulation, which one is observation. But I can tell you that the blue ones are real observations, and the red ones are from simulations. And perhaps you can barely tell if there is any difference or not. And other than from our eyes, there are methods to quantify the similarities. And this picture of basically evolution, or this standard model of cosmology, has been very, very successful in explaining the large scale of the universe. This is those, you can easily recover the very complicated filamentary pattern that we call cosmic web through the simulations. But all the simulations that I've shown you, well, I talked about dark matter. I showed you the distribution of dark matter. But other than some indications in the CMB, where else do we find dark matter? Why should we believe that dark matter exists at all? Explain 4 different observations that indirectly can tell us that dark matter exists, or actually some missing matter exists. So, number 1, when we look at a cluster of galaxies, actually these observations were made even in 1930s or 40s. When we look at clusters of galaxies, which are very big groups of galaxies, sometimes there are thousands of galaxies in these clusters. When we look at these clusters, of course we see the galaxies, and we can measure the lights, and we can, from the lights, we can estimate how much mass, this luminous mass, how much mass exists in these clusters. On the other hand, we could observe their velocities. Velocities are very critical in my slide and in general in this field. Velocities can tell us about the mass that exists in that object. If you look at a galaxy, a cluster of galaxies, a group of stars, if you look at their velocities, either in the sense of rotational velocity or the random velocity, these can tell us about how much matter exists in there. Basically, it's like from the speed of Earth around the sun. If you know the distance of Earth to sun, you can tell what's the mass of the sun. This is more or less similar idea. If you look at the velocities in the systems, you can know how much mass is there. So when we look at the velocity of the objects in that cluster, we'll see that we recover a lot of mass. We need, now you know, we need about 5 times more mass than what we observe. So there is 5 times more mass than these little dots of galaxies. So there's some missing mass over there that the galaxies are moving with a high speed. Similar idea exists when we look at usually spiral galaxies. Observations were made for Andromeda galaxy. This is similar idea. This is velocity versus radius. If Andromeda galaxy, what we observe is everything that's there, the velocity should have been changed like the red curve. But what we observe is actually the white one. You'll see there is not a negligible difference between the two. There are significant differences. Again, this tells us that there's some missing matter there that we do not see. We can also detect dark matter through gravitational lensing. General relativity of Einstein tell us that light bends in the space-time, and the clusters of galaxies act like a lens, and you'll see these arcs. Right? These arcs are basically effects of bending, and from analyzing these arcs, we can tell how much mass is there. Again, we recover there's a lot of mass, more than what we see. And one very exciting one, I try to explain as much as I can, or the better I can, is the bullet cluster. First of all, if you ignore the colors, you'll see 2 population of galaxies, which are basically 2 clusters of galaxies. If you look at the gas is basically in the red region. And gas usually follows where the mass mostly is. So from looking at the gas, which is basically follows where the most mass is, you can say that the most mass is in the middle. But again, through lensing, you can say that most of the mass is in this blue cloud. This shows that there's a separation in where the gas is and where the most matter lies. And this is again another indirect way that tells us that there is some dark matter that we do not see. That there is some missing matter that we do not observe, but it's there. But apart from this dark matter, let's say cold dark matter. So we're not that cold here. So what's this coldness mean? Essentially, what cold dark matter, or some people talk about hot dark matter, this coldness or hotness tells us about what's where the velocity of the particles in the early universe. Cold dark matter means the particles had relatively low velocity, but in the case of hot dark matter, it tells us that the particles had kind of high velocity. And all the simulations I showed you so far is the cold dark matter. If I do similar thing with hot dark matter, we'll realize that the structures that we see doesn't look like observations at all. That's why it was kind of early in cosmology, in 1980s almost, that people realized that hot dark matter cannot be the case. Cold dark matter is the standard feature. That's why lambda cesium has a cold component in there. There are some features for this cold dark matter. I would like to emphasize them because I need them in the later slides. Hierarchical growth of structure. What it means is that in cold dark matter, first you start to form small objects. Small objects merge together, they form bigger objects, and these bigger objects merge together and form bigger and bigger objects. So the structure basically, we call it growth from the bottom to top. Small things first, you merge the small things and you make the bigger one. I have another movie that shows a similar idea, but in a more beautiful way. This is simulation of a galaxy a halo of a galaxy that looks like Milky Way, you can barely see there's very faint, smooth structure here. But as the time goes by, the time is moving forward, you'll see that you'll start to see small clumps are forming. By the way, the camera is rotating around the object. That's why you have a kind of a rotation element here. And you see now you have a little bit bigger structure. And you can see these bigger structures are merging together. And very exciting stuff is forming. Still, there are small clumps that are joining the main galaxy. Our galaxy doesn't have very smooth or calm formation. This is what happens to most of the galaxies in cold dark matter picture in our standard cosmology. That there are a lot of things happening. And you can see how much is passed from the beginning of the universe. Beginning of the universe was 14 gigayears, which is billion years, 14 billion years ago. And we are at about like 8 gigayears now, or 8 billion years. And we are almost getting to the present time. Okay, we're almost there. So this is how the halo of our Milky Way, so that we live in, forms. By the way, when I refer to the term halo, I basically mean the dark matter distribution in this object. So eventually Milky Way would be sitting somewhere close to the center, and you will see there is a lot of small objects, small clumps of dark matter are in the environment that are either merging or rotating around. So this movie was done actually in 2005, and at the time it was done, it was one of the best, I guess the best that people could do at that time.
Hazzy?
Yeah.
Sorry. Could you just talk about the Z that was under the
Oh yeah, of course. Sorry,
I should know.
Oh, don't worry.
Maybe
Let me play the movie again and well, it's so Z, that's basically decreasing. Z is eventually we call it redshift. The idea of the redshift, you might call it as also as Doppler-less redshift, is that when an object is moving away from you, the wavelength that you reach gets stretched through time, through the object getting away from you. The wavelength gets stretched, and the wavelength getting stretched means the object or the light that you detect has shifted to the redder wavelength. And when we look at galaxies in time, basically, you remember the redshift surveys, you look at a patch of the sky, and you look at a lot of galaxies. The ones that have very high velocity means they have very high redshifts, and they are at the early times in the universe. But the ones that are closer to us are moving with a lower velocity, so the redshifting is smaller, so it means it's recent years. So Z is basically 1 at now, and as you go back in time, or as you look at galaxies back in time, the redshift goes higher and higher. In cosmology, it's a measure of time, basically, that cosmologists like to use redshift as a measure of time. But basically, these two are equivalent. You can just convert between them. Okay, so another feature of the cold dark matter, kind of exciting, was done by 3 astrophysicists, Julio Navarro at UVic at I'm sure most of you know, Carlos Frank, and now working in Durham, England, and Simon White, at the time at Cambridge, but now at Germany. So these three scientists, I was privileged to be working with Julio, he's my supervisor, and also Carlos Frank. I guess I'm going from left to right. The next target should be Simon White. So these people, and also they're standing by their height, I guess I'm also moving this direction. So these three people, they've done a lot of extensive work in cold dark matter picture, our standard cosmology. They realized no matter what the object size is, in a very small galaxy, up to a very big cluster, no matter how big this object is, the mass distributions are almost similar, and you can describe it with a relatively simple formula. Well, simple formula, if you look at a cosmology formula, this is like a simple. It has three parameters, and basically you can describe all the cold dark matter halos with this basically formula. This is very powerful. I guess I built my whole 5 years of PhD based on this. And how this formula behaves, basically it tells, sorry, I forgot to say, rho is the density. It's density of the matter. And that formula kind of looks like a blue curve that you see here. Basically, this is the center of the halo, or center of the galaxy, and you move outwards. The density is high in the center and lower in the outer parts. And what is important is that around the center, the density basically has what we know, it has a slope of -1, or it's basically increasing towards the center. It's not flat like this case, that I will reach to later on. But this is the NFW that is basically the prediction of the cold dark matter picture. This is critical. This will introduce challenges to lambda CDM later on. I will get to that. I talked a lot about dark matter. It's time to talk about where the galaxies are in this framework. Everything was dark so far, dark energy and dark matter. So I told you that we have basically halos of dark matters. Halos of dark matters are close to galaxies. Galaxies that we see today live in the very center of the dark matter halos. And basically, if you remember from the movie, everything is merging together. So when the dark matter and all this stuff are merging together, the gas also comes with the dark matter. This is a very cartoonish picture of that. The gas also comes to the halo. The gas sinks to the very center, and it can form stars, and all the galaxy formation that we know of happens in the very center of the galaxy. But the galaxy is embedded in a much larger dark matter halo. This is the picture of the galaxy that we have today. But the point is that galaxy, like the Milky Way that we see today, is not very alone like that. We know that it has companions, and I guess its two big companions are large Magellanic clouds. They lie in the southern hemisphere. If you unfortunately cannot observe them from the Canada, I guess I'm sure you know better than me that if you go to southern hemisphere, you will see these beautiful clouds. People used to call them clouds because they didn't know what they are. But now we know that they are galaxies. They are smaller galaxies. They are companions of the Milky Way. They are orbiting the Milky Way, but they are much smaller size. They are almost 100 times smaller than our own Milky Way. But these are not the only two companions that Milky Way has. We call these satellites of the Milky Way because they're orbiting the Milky Way. The picture we have today is more or less like here. Milky Way sits in the center, and you have a few tens of little companions, dwarf galaxies, which are satellites of the Milky Way around them. I'm sure some of them have to be mystery objects, but unfortunately I don't know their numbers. But I have the names, or we can talk later on. I'm sure there's just some of them are observable in smaller, small instruments that you might be using. So these dwarf galaxies, which are basically the title of my talk is called dwarf galaxies. Now we get there. These dwarf galaxies are small galaxies, and They come in different shapes and morphologies, like normal galaxies. So this is LMC. It has, we call it irregular. It doesn't have any specific morphology or shape. It's an irregular galaxy. Some of them, like this one, have spiral patterns and have these key structures. These are more the larger ones. Some of them, like this one, are like blobby, very smooth, no detailed structure. We call these ellipticals. And some of them, like this one, you can barely see that there's a very diffuse component at the center of the image. This is Fornax dwarf galaxy. Actually, most of the dwarf galaxies look like this. These are very faint objects in the sky, and that's why they're kind of hard to detect. And it's been the last 10 or 20 years that we could detect a lot of them because they are faint and they diffuse in the sky. And why these dwarf spherical galaxies are important? Because they introduce some challenges to lambda CDM model predictions. I'm going to introduce to you, forgot to keep the time. Oh, did someone keep the time? How much time I have? Okay. So I will introduce 4 challenges that have been known for about a decade about lambda CDM. And some of them are weaker or stronger than the other ones. I will review these challenges, and I will show you the work that I have been doing in my PhD, of course, with my colleagues, to see what we could do about these challenges. Can we say lambda CDM or not? So one of the striking things that we see in lambda CDM, you saw a simulation of a Milky Way-sized galaxy, and this was how it looked like in the dark matter distribution. And this is how it looks like if you look for galaxies. The very clear difference is that there are hundreds or even thousands of small clumps here, but we'll see only 20 or 30 dwarf galaxies around our Milky Way. This has to be known as the missing satellite problem, because why not all these small clumps are hosting these small galaxies? Why doesn't Milky Way have thousands of these satellites? Why does it have only 20? This was known kind of early time when the lambda CDM was brought up, because the simulations all show that there should be a lot of mini clumps around the galaxy, around Milky Way, but we do not observe any. So missing satellite problem. And what else do we see? Later on, people again realize that there's another difference between what we observe and what we simulate. Again, this is a simulation that you saw before. Here, you have Milky Way at the very center, and these are its the other circles are its bright satellites. I kind of rotated its coordinate such that you see the satellites in a line. What it tells you in 3D is that everything is on a plane. You can imagine you have a disk, and you look at the disk from the very edge on you. You kind of see a line. Does it make sense? So what it tells you is that the bright satellites of the Milky Way are on a plane. They have a planar structure. But if you look at the simulations, you see everything is more or less random. You do not see any planar structures. And people have been trying to get these planar structures out of simulations for maybe 10 years or so. And they find that it's very rare.
Is the plane in the same plane as the galaxy?
No, it's
different.
Kind of perpendicular. So the plane of the galaxy is here, like coming out of the board, and the other plane is kind of perpendicular to that. So this was called as a plane of satellites problem. That is it a normal configuration in the lambda CDM or not? Does it make any? Some people are still like, there are papers coming out every month or so that people are still arguing that this could be a challenge for lambda CDM. Now let's go to the third block, the third problem. The third problem relies on that NFW profile I told you. The black curve here is the NFW that you saw before. Something about dwarf galaxies is that they are very dark matter dominated. What it means is that when we look at their again, velocity of the stars or gas, we can tell how much mass is there. And dwarf galaxies are among the most dark matter dominant objects in the universe. Sometimes they have up to 100 or thousands times more dark matter than normal matter. It means they are very ideal places to look for how dark matter behaves, because the normal matter could kind of interact with dark matter and change its prediction. But if you find a system that is full of dark matter, you kind of say, okay, I ignore the very small component of normal matter and I study dark matter in those systems. And people have seen that in the, actually it has been derived from observations, that if you look at the density profile of dwarfs, they look more like these colored lines. So other than rising to the center, they kind of flat out to the center. This is what people call core. The name is a bit counterintuitive. The ones that have a constant density in the center are called core galaxies, and NFW is called, it has a custody profile or custody behavior. So this has been actually one of the most important challenges for the Lambda Stadium, because this was a very, the NFW work has been very clear about how dark matter should behave. And we expect a black hole, but why galaxies behave like that? And if I skip the next problem, now we have to basically answer this question: what's happening? Is anything wrong with Lambda Stadium? Do we have to have alternative models instead of these standard cosmology pictures that we have? People have been proposing different way out of it. One is that going to warm dark matter. What it means, I told you what cold dark matter is, and I told you what hot dark matter is. We know that hot dark matter doesn't work, but people say instead of cold, it's a little bit warm. These are two ends of the spectrum. You have hot dark matter, which is not working, and you have a cold dark matter, which has been super successful so far. Maybe we have to be a little bit warm. So people have been working on these warm dark matter models, but it has not been successful as cold dark matter in explaining everything. Cold dark matter, basically, other than these very small objects, cold dark matter explains everything. Now this idea is very recent, maybe like within a year or two, that people have been working on self-interacting dark matter. The cold dark matter that I told you, they just interact gravitationally. There is not much more going on. That's why they do not emit light, for example. But people have been playing around with this, how dark matter interact with each other. Actually, at the particle level, dark matter could annihilate like any other particle, but in a bigger picture, they're just gravity. But people have been playing around with these models. It has been very new. I cannot say if it's working or not, but this has been another model. But way beyond all these models is modified Newtonian dynamics. So some people say, what we know about dynamics, what Newton and Einstein have been saying, they only work locally. If you go to larger scales, the dynamic doesn't behave the same. We should change the law of gravity. Gravity is not gm over r squared. It's a bit different. This is people again have been working on the MOND for, I guess, a couple of years, but it's still very, very new. You want to get rid of 200 or 300 years of dynamics, and you want to build something very new. So it couldn't, so far, it couldn't be as successful as Lambda Stadium. MOND could kind of, sometimes, I'm not an expert in this, so I tell you my overall knowledge of that. People could explain individual things. For example, they could explain galaxies, or they could explain clusters, or they could explain scales. But the combination of these things, people have not come up with any theory like that. So again, it's not as successful as Lambda Stadium. The way out of these challenges, that's actually very important, it's not negligible, is that All the simulations and theoretical works I had shown you so far, or all those challenges, they've been purely dark matter simulations. So you're ignoring what the normal matter that stars and galaxies are made of. You ignore that component, and you only simulate cold dark matter, or you only simulate dark matter. Of course, on the very large scales that the dominant factor is dark matter, you do not see any effects. But why should it be the case in smaller scales? On a smaller scales, normal matter could be as important as dark matter, depending on what scales you're looking at. So this is a very interesting and exciting way to look at and trying to understand what's going on. Although it's very, very difficult. Why? Because the simulations of dark matter are very simple in the sense that the dark matter, I told you, only interacts using gravity. Gravity is what merges things together. But if you introduce normal matter that we are made of and galaxies and stars are made of, the picture is not that simple anymore. You have gas. The gas has different chemical components. It needs to be able to cool or heat. It needs to be able to form stars. Stars are evolving. They make all sorts of exotic things like supernovae, and we have black holes. So the whole picture is very, very complicated. That's why simulations or theoretical work based on this galaxy formation couldn't evolve. Maybe not very straightforward or not very quick. And this is the field that I'm working on, and some other colleagues are still working on these galaxy formation models. We're trying to put in our simulations as much as and as accurate as we could these galaxy formation models. So my project that's related to the local group, let me introduce you to the local group. The environment that we live in the universe is our own Milky Way galaxy, is our neighbor Andromeda galaxy that looks like this. These are two big galaxies. And you have a bunch of small dwarf galaxies and satellites in this environment. And there is not very big objects in the immediate nearby. This is a very ideal place to study cosmology because it's nearby, and you can detect these dwarf galaxies that are potentially introducing challenges for our Lambda-Sibbian picture. So we would like to study this environment because we can observe dwarf galaxies with very high accuracy, well, relatively, compared to further galaxies. We see most of the dwarf galaxies in this environment. That's why I would like to study this environment, and we introduced this project that I have been working on for my PhD, the project of simulating the local environment, or a project for simulating this local group of galaxies that we know of. What's new compared to other work? First of all, to be able to resolve these small galaxies, we should be able to do very high resolution simulation. These galaxies are small galaxies. We should have a high resolution, but we would like to have a cosmology picture. We do not want to simulate a single galaxy. We would like to have the whole environment and the whole cosmological picture, but we would like to have a high resolution as well. Plus, we would like to include the galaxy formation model that I mentioned before. We are using, nowadays, there are almost two competing groups working on this galaxy formation model. Both are having very exciting models to simulate the galaxies. One is the group that I'm working with, is of course my supervisor, and some other people are based in Europe, more in Durham, UK, and also in Leiden of Netherlands. And the other group is based on US, mainly in Harvard and California. They are both making exciting galaxy formation models that we could use. So the one that I use is called Eagle. It's called Eagle Galaxy, the Eagle code or Eagle model. It has different components and one of the best of its time. Not the best of all the time, but the best of its time. We have the gas that gas can cool. It can form stars. The stars can evolve. and make heavier elements. You know, at early the universe, we only have hydrogen and helium, but the stars can make heavier elements. The stars can explode as supernova, and the supernova explosions, you know that because these are explosions, they affect their environment. So we make sure that this interaction is included in the simulations. Chemical enrichment, I told you about that. Other than hydrogen and helium, you're making heavier elements. And we have supermassive black holes. You know that the center of the galaxies, there are supermassive black holes that they could affect the galaxies a lot. So these are the main components of our simulations. And I thought I had a movie that is, yes. So in this movie, it's not my simulation yet, it's the Eagle simulation. You have the dark matter evolving, you have gas evolving, these are stars. And for now, again, we can ignore that picture, this is high density gas. So you see there are exotic things happening, and what happens in dark matter and gas and stars, they are very different. They behave very differently. This is dark matter, things merge together and make a bigger object. You see the gas and the color show you the temperature. Oh, hopefully it starts from the beginning. Yes. So the temperature, the red color is higher temperature, and bluer color is colder. And this is where the stars are forming. And you can see how different, basically, the universe that we see is different if we could see gas and dark matter. So this is the galaxy formation component. As I mentioned, we would like to have high resolutions. Oh, I missed that. So these are some galaxies that came out of that Eagle galaxy formation model. That you can, it's fair enough to say they look like real galaxies. And it took astrophysicists to reach their model maybe for 4 or 5 years. 4 or 5 years ago, our galaxies didn't look like any of real galaxies. But nowadays we can simulate the universe or the cosmos, and we can find galaxies that look like the real galaxy. This all actually is the Hubble tuning source you're familiar with. You see elliptical galaxies, S0 type galaxies, spiral galaxies with bars, and non-bar spiral galaxies. This is very impressive. So we're kind of happy with our galaxy formation model. How can we improve our resolution and get a better resolution of what we want? So for those of you who like technical details, so we simulate a very big portion of the universe. Again, this is the cosmology box we call. We simulate the whole universe, but there are some techniques that we can put our computational power in a small region. So most of the computational power is on this small region, but we simulate the whole thing to make sure the universe is evolving as the real universe in lambda stadium. Our simulations are mainly done in Durham, in UK. These are computer clusters of computers that we use. You'll see Dr. Lydia Heck, who's the IT manager for this cluster of computers. This is only one row of computer. There is at least 2 more rows. There are more than 2,000 CPUs in these clusters of galaxies. Sorry, clusters of computers, not galaxies this time. In this cluster of computers, and I was just making the estimation for myself. We run one of our simulations. If we run one of our simulations on this cluster on 500 cores, it takes about 1 or 2 months. I did a simple calculation. If you want to run it on your laptops, apart from the fact that you need a huge amount of memory, it wouldn't fit in your laptops. But imagine you get rid of the memory, you just use the CPUs in your laptops. It will take about 100 years to run. But we run it on a cluster of computers, again on 500 cores, again one of them, and it took 1 or 2 months. So it was not that bad in the past 2 or 3 years. We could run a bunch of them. And when I say 1 or 2 months, this is 1 or 2 months of straightforward running. And you know, in practical terms, 1 or 2 months becomes a year when you have to deal with little issues of practical terms. So this is very impressive. Actually, this is one of these clusters located in Institute for Computational Cosmology in Durham that Carlos Frank that I mentioned is head of. And I traveled there and I saw that computational room. That was pretty impressive. They're working all over the year 24/7 and they run simulations like what I showed you. So what comes out of the simulation looks like this in dark matter. This is the picture you saw before. You have Milky Way and M31. You can call it whatever you want. One of them is Milky Way, one of them is M31, and a bunch of dwarfs. And in dark matter, this is what we see. So there are two main galaxies, which are potentially hosts for Milky Way and M31. And as you expected it, there were hundreds or thousands of small clumps of dark matter everywhere in the universe. And this is a similar picture, just a different orientation. This is a dark matter distribution. And see what happens if I look at the stars. So these are where the stars are in our simulations. Most of the universe is empty of stars. So not all those little clumps are forming stars. There are physical reasons behind them. They are too small to be able to retain or cool their gas, and they are very sensitive to their environments. But there are reasons why those small clumps are not forming any stars. But the stars are forming in the big halos or big clumps, which would be the two main galaxies, and you'll see a bunch of dwarf galaxies around them. And if you look at the gas, it's hopefully turning into gas. The gas is behaving differently. You have, again, a big kind of halo of gas, but in the very center, these are disks of the galaxies, the two Milky Way and M31 disks of galaxies. You'll see this kind of warm kind of shape. This is a smaller galaxy that's falling into the main one. And because it's falling, it's losing its gas. And I want to show you a picture of this galaxy that's potentially like a Milky Way. And you can see this is impressive. It looks like a Milky Way. You have spiral patterns and you have a disk. So this is a basically spiral galaxy that you're looking at face on or edge on. And you can see a dust plane in the middle that's like very striking and very interesting for those of you who look at real observational images of the galaxies. There are dust in the galaxy. So that what you see like a bit dark in the middle is a disk of dust that's obscuring the light from the galaxy. Very impressive. The other exciting thing about the lambda CDM that we also recover in our simulations is that in lambda CDM, you saw the picture that everything is collapsing together and making a bigger object. And because things are collapsing all at the same time, they make stellar halo, what we call halo this time. Stellar halo, this is a very diffuse component around the galaxy. So imagine that the Milky Way or M31 is living in the very center. If you be able to see that diffuse stellar components around them, you will see that they have very complicated structures. There are streams of stars, there are these shell-like features, and actually this is again another satellite that's falling into the main galaxy and it's making a stream of stars. And recently, I guess 3 or 4 years ago, that observers looked at the Andromeda and they could deeply look at this stellar halo around the Andromeda. This is an Andromeda galaxy in the center that's saturated. But you see a very diffuse components around. And if you look carefully, you see, again, shell-like, stream-like features. These are very hard features to observe in further distant galaxies. But because Andromeda is quite close, you could observe it. So this is what's totally expected, and we would like to see things like that in real galaxies, because lambda CDM predicts that. Now let's go back to the challenges. I think I've already convinced you that the dark matter picture is different than the stellar component picture. You have hundreds of clumps here, but you have maybe tens of galaxies that have stars in them. So this automatically solves the missing satellite problem. So in the real universe, if cold dark matter is the right picture, not all those clumps form stars, and also only the bigger ones form. And most of the universe is free of basically dark. And in terms of numbers, for those, we need to basically quantify if these numbers are consistent with what we observe. And this is in very good consistency with observations. The number of dwarf galaxies that we observe in the local group in a fixed volume is very, very similar to what we make in our simulations. I don't go to the details of the charts that I don't like. So the black line shows you the observations, and the other colored lines are our simulations. So our simulations are, this basically shows you there are about 100 galaxies in the local group. And our simulations are making similar number of galaxies. So the missing satellite problem seems to be easily solved. Let's look at the plane of the satellites. In our simulations, we have 24 Milky Way-like objects. So we have 24 objects that are potentially analogous to Milky Way. And one of them has a plane that's very similar to the plane of the Milky Way. Unfortunately, I didn't have a better picture, but here in the very center is that Milky Way analog, and this white circles you see is its brightest satellites. This is very similar to the plane of the satellite I showed you for the Milky Way. And I must say we didn't have any biases or pre-selection that would give this to us. It just naturally raised out of simulations. 1 out of 24 have such a plane. So it's not an extreme challenge for the lambda CDM. It's not a common configuration, but it's possible. Sometimes, every now and then, based on these very low numbers, statistics, 1 in 24 could form such a plane. So we're fine with that too. The other exciting result is that this plot shows you the stellar mass versus the halo mass, basically the stellar mass versus dark matter mass. What we get in our simulation and what we observe. I'm sorry if the symbols are small. The triangle black symbols are observations, and the other symbols that you see are coming from the simulations. People had difficulty in the past to bring the simulations and observation in agreement. And again, without any specific tuning or pre-selections, the dwarf galaxies that come out of our simulations are pretty consistent with what we observe. But the Corpus problem. This is a bit tricky. None of the dwarf galaxies in our simulations are having core. So the dwarf galaxies in our simulations all look like the black one. None of them have this chord feature or this flat feature in their density profile. So what's going on? The first honest answer is we don't know. But second, some people like my supervisor, they believe that what we observe is very kind of hard to interpret. This is not that we directly observe. We have to observe velocities, then from the velocities get some mass and infer some kind of density, which in practice, this is a very messy process. This is not very straightforward. It's straightforward in concept, but in practice, this is not very straightforward. So some people, like my supervisors, think this is what we see as core is actually what we have misinterpreted data, the actual data of the real universe. But the problem still stays there and it's still open. People are working on it. Some people who claim they solved this problem, they have some a little bit exotic galaxy formation models that they could change the dark matter distribution and they could explain this core problem or this core behavior, but not in all the cases. Actually, my colleague, the other PhD student that is working with us, turned the problem in another way. Any curve that you see here, not the actual points, the curve that we see here is actually the NFW. This is another way of showing NFW. This is circular velocity and radius. So NFW is always kind of very well behaved. But if you look at the actual data, they are all very diverse. So we can turn the forecast problem into another problem, that the rotation curve of galaxies that are essentially telling us about density and mass are much more diverse than what we see in a lambda-CDM universe. So what did we find so far? From the four or five challenges that I introduced to you, we could solve 3 of them. And solving means they have answers. If you include right galaxy formation models, you could explain why the previous challenges are not challenged anymore. But this forecast problem, or this diversity of rotation curve, still is an open problem that we are working on. This work is, I forgot to credit this speaker for Kyle Oman, is another PhD student here working with us. So I hope that I could convince you that lambda-CDM is very successful in larger scales, explaining CMB and explaining a lot of details. But when it comes to the small galaxies, which are dwarf galaxies, it introduces some inconsistencies or some questions that some of them seems to be more or less easily solvable, and 1 or 2 are still debatable. And the other takeaway point I would like to make is that the computer simulations that we do, or of course other astronomers do, they are very key components to the studying galaxies and cosmology. I mentioned at the beginning that galaxy formation is not something that you can solve on pen and paper. You need very sophisticated numerical models that you will simulate with computer simulations and clusters, and hopefully in the next few years, or maybe in the next decade, we have better answers for these challenges. Or maybe we have to change our standard picture of cosmology. Thank you, and I'm open to next questions.
Any questions for Azzy?
How much does it cost?
To make those clusters.
How much, like, what, I was looking at those computers, and, like, who's funding all of them?
These are usually national funding. This is not almost maybe impossible to build on private funding. There are some clusters in Canada and some in US and Europe. All that I know of, they're funded by national grants. But if you want me to give you numbers, honestly, I don't know.
Well, this business you mentioned, modified Newton dynamics. If they fudge around with the Newton dynamics, can they get away from the requirement for dark matter and dark energy?
I'm not very good about it. I know for some of the individual cases, like rotational velocity of the galaxies or clusters of galaxies, for these individual cases, they could produce basically something. They could remove dark matter and still explain the observations. But for the dark energy, I think they're still fighting with the models.
A while back, they published a study on black holes, because it was at the time, it was the first survey done in a dwarf galaxy.
Okay.
So they basically showed that in a dwarf galaxy, the black holes were less numerous and smaller than they were relatively in a larger galaxy.
Yeah.
But they only had a base model of 1 at the time. Has there been any surveys since then on black holes in dwarf galaxies?
I'm not exactly sure what the survey you're mentioning, but nothing very big that I've heard of recently that they have set up new ones. But what people have been observing is that the bigger the galaxy, the bigger its supermassive black hole is. So you naturally expect that if you come to small scales of dwarf galaxies, their supermassive black holes will be also smaller. But honestly, I don't know about new surveys. Yeah.
This is not quite in your area of work, but it
It's okay.
occurred to me when I was watching what you were showing. We have the hierarchical model of the universe where there are fairly large scale agglomerations of dark matter that are occurring. But that implies that entropy is increasing in those portions of the universe locally.
Right.
Large scale, but locally still. But we know from the laws of thermodynamics that entropy must overall increase. So what is going on elsewhere in the universe at these large scales that still is enabling entropy to increase? And is this in some way related to dark energy and dark matter?
Very exciting question, and let me see if I can answer that. So you're totally right. In smaller objects, the entropy is increasing, and if it's increasing somewhere, well, I think it makes sense. You expect that with the evolution of a system, the entropy can always increase. It cannot decrease. So it's I guess expected that if you make a system evolve, the entropy is increasing. But if it's decreasing somewhere else, the honest answer is I don't know.
Okay.
We have a physicist over there. I think you know. I get some help.
Well, it's just that it's always globally measured, right? So whenever you have the structural formula, yes, you're increasing the entropy over there, but in the void that's compensated in those ways because it's extending. So you're creating more void as I guess it's compensating for the
Because of the expansion.
exactly.
Yeah, okay. I guess there's nothing really mysterious about it. I hadn't been really aware of the large scaleness of the operations. That's really kind of remarkable in a universe where entropy is otherwise increasing.
That's true, and the fact with entropy is that often people forget what is the full scale that is taken, because the local entropy can decrease, but the global one, and you have to be careful in how you define global entropy and what are your boundaries of those things. So it's quite technical and abstract. People use it actually to define the arrow of time, how it's coming home. It's the way energy flows.
Other than mentioning it in passing, we really haven't discussed dark matter, or dark energy, I should say, in this study. Does it have any play in what you're doing or not?
I was going to comment at the beginning that the dark energy was, I think it's fair to say it's one of the most important questions in cosmology and physics that we do not know what it exactly is. The role of dark energy in these simulations or the work that I'm doing, dark energy sets the expansion rate of the universe. So what we need to know in this simulation is what's the rate of expansion. Then the structures are usually growing using how dark matter is behaving. So perhaps if the dark energy is actually there, the only thing that we care is what's the expansion rate, and it's not affecting our work much. Yes.
Another question, maybe more related to your area.
Yeah, of course.
You talked about the chemistry
Mm-hmm.
of supernovae and what is going on. And it just strikes me as hard to imagine that the formation of iron and other chemicals has very much to do with how dwarf galaxies form. But can you maybe explain that? Explain why the chemistry might be important.
Why the chemistry might be important. So the importance of the chemistry.
Because physicists don't like chemistry. Chemistry is not important.
Oh no, it's important in our way. It's a small factor, but it is still important. The place where it plays its important role is in the cooling of the gas. If you have only hydrogen and helium, the gas has a hard time to cool down. But you need to be able to have basically higher, the heavier element and also molecules and atoms, other atoms, to be able to cool the gas efficiently. That's where it plays its important role in our simulations.
Excellent.
Very nice, Nancy, thank
Thank
you.
you.
Small gift token right there.
Oh, thank you.